Let's talk about drag, or sometimes called resistive force, or air resistance. Any of these words work perfectly fine. Now in AP Physics C, the resistive force model, is a simplified model of real drag, and is this. The resistive force, I'm going to call F sub R, you could call F sub D for drag if you want to, that would be fine, is equal to negative kV. So what does all this mean? The negative means that the force goes in the opposite direction as velocity. So that's what makes it a resistive force. This equation also tells us that as velocity gets larger, the resistive force gets larger. And that's what makes this an interesting and somewhat complicated topic in AP Physics C. Now, real drag is expressed by this 1/2 CD rho A V squared V hat. So again, we've got that negative to indicate that the resistive force goes in the opposite direction as velocity. And then all this stuff here is kind of doing the job of the K there. This is all, these are all constants that are going to be related to the particular circumstance. So A is the frontal area of the object. The bigger the object is, obviously, the more drag force it's going to experience as it travels through the air. CD is the coefficient of drag, or the drag coefficient. This is based on the shape of the object. So when you say that object is very aerodynamic, you're saying it has a low coefficient of drag. Rho here, this is not a P, this is a Greek letter rho. This is the density of the air or whatever other medium you're traveling through. So this doesn't only work for air resistance, it works for water resistance. It works for the resistance through any fluid. If you're traveling through any fluid, a fluid could be a gas like an atmosphere, or it could be a liquid like water. So for water, one of the reasons it's so much harder to move around quickly through water is because the density of water is so much greater than that of air. On the moon, you'd experience much less drag force because the density of the moon's atmosphere is essentially zero. Additionally, airplanes like to balance between being able to generate lift and having low drag. So this is one of the reasons that commercial airplanes or long-distance airplanes often fly at rather high altitudes, like 5 miles, because there's lower density of air the higher you go in altitude. However, of course, they have to balance between having enough air density to generate sufficient lift and having low drag so that they can reduce fuel consumption and increase efficiency. So this is a better model than this. This model is real. This is called viscous drag, and it does exist at all speeds, really, but this gets completely dominated by this almost immediately. It's only at very, very, very low speeds that this is the primary source of drag. For anything you'd actually be talking about, this is a much more realistic equation for drag. However, the mathematics associated with this quadratic form of drag is much more complex. So to balance between realism and doability in terms of the mathematics, we use this model in AP Physics C. Now, in order to analyze this model, we're going to use basic differential equations. So if we take this model down here, and let's apply it to an object. Let's say it could be a bullet that is shot into a gel block. It could be a box on a, let's say, frictionless surface that has been given a kick, so it has some initial velocity, V0, going that way, and there is an atmosphere. So it's going to experience some air resistance as it travels to the right through this atmosphere. And this bullet obviously is going to experience resistance as it travels to the right through this gel block. So these are the types of problems we're going to analyze. In this video, I just wanted to introduce this model and that model as well, while also explaining why this is the one we're going to be primarily analyzing. Again, the mathematics here is doable. The mathematics here is much more complex. By the way, note, This is a v hat. All right, here I don't want to put a velocity symbol on this v squared. I just don't like the way that looks. So I put a unit vector right here to indicate direction. Right? That's why that minus actually, or that negative actually makes sense. This is a vector. This is also a vector in the direction of v hat. Remember, the hat means unit vector. So it's a vector that gives us a direction without changing a magnitude. That's why unit vectors are useful. Until next time.